There we go. So we have a nucleus and a nucleus, and in between them we have some shared electrons, yes? What does the positive nucleus do to the shared electrons? It attracts, right? So I've got the positive nucleus attracting to each of these shared electrons. So a covalent bond is the attractive force between the nuclei and the shared electrons. BW is between. Whereas an ionic bond is an attractive force between the negative anion and the positive cation. It's always going to be, every bond is an attraction between a positive and a negative. It just depends on what's the positive thing and what's the negative thing. Yes? Yeah. Mm. Because there's not just protons present, there's also electrons. There's also those core electrons that are in between the nucleus and the bonding electrons, because the bonding electrons are always in the outer shell. Okay, I'm not going to talk about that too much because now we're getting into the whys of it, and I just don't want to go there yet because otherwise, like, tangent. Do you know what I mean? We will go there though, I promise. Cross my heart. Okay? So, an ionic bond is the attractive force between the positive cation and the negative anion. The reason I'm bringing this stuff up now is because we are going to be looking at intermolecular forces, which involve knowing what a dipole is. Okay, this is going to be in the next unit coming up, but I wanted to make sure we had sort of hit on this first. Yes? So if we had to label our two ends of the hydrogen chloride, what would we label the hydrogen? What's that letter? Delta. It's a lowercase delta. Okay? And I would write delta what? Delta positive, because it's going to be slightly positive. The chlorine, what would I write beside the chlorine? Delta negative, because it's somewhat negative. It has a partially negative charge. And if I wanted to draw the dipole arrow, what would the dipole arrow point towards? Would it point towards the hydrogen or would it point towards the chlorine? It would point towards the chlorine because it always points towards the more electronegative. It points where the electrons are being pulled. Okay, that's the pulling of the electrons. And what do we put on the end of the dipole arrow? We put a cross, essentially, because that's like our little plus sign. It shows the positive end of the dipole. Okay? And that's about all I want you to take away from this at this point, is that you can compare electronegativities, and if they are different from one another, you will have a polar bond rather than a nonpolar bond. So if we were to look at, say, let's say I bonded sulfur and iodine, what kind of a bond would they have? Sulfur and iodine. It's going to be covalent because they're both nonmetals. Is it going to be polar or is it going to be nonpolar? These values here, these numbers, are the electronegativities. That's going to be nonpolar because There is no difference. They both have the same electronegativity. Yes. If they ever get to the point when it's essentially nonpolar, okay, there are like little cutoff points. If we look towards the bottom of the page, you can actually say that if the difference in electronegativity, the electronegativity difference, if it's less than 0.4, then the electrons are shared essentially equally. Okay, so even if it's not perfectly exactly the same, like 2.5 and 2.5, if I had 2.5 and 2.2, the difference is only 0.3, we would still consider that to be a non-polar bond where the electrons are shared equally. You can see that the density is similar across the atom, okay? Or sorry, across the molecule. The moment you get into a difference that's bigger than 0.4, all the way up to about 1.7, then you get into unequal sharing, but you still have a covalent bond. The electrons are being shared. One thing has not completely taken it away from the other thing, but you will end up with a positive end and a negative end. If we wanted to draw the dipole arrow for this thing here, what would the dipole arrow look like? Which direction would it point? It would point to the left. Okay, that would be our dipole arrow. You are not responsible for really memorizing like the 0.4 and the 1.7, okay? At some point, like on the AP exam, you're not going to get those numbers given to you, so they're not going to expect you to memorize them. They're going to expect you to know overall trends. Like, where are the most electronegative things? Top right. Where are the least electronegative things? Bottom left. Yes? Like, S-I-2. Yeah, it doesn't matter. Yeah, because, so let me see if I'm getting your question right, and then tomorrow I'll come to you. The question, I think, and correct me if I'm wrong, is if I have S that's bonded to two I's, does that affect the polarity? Is that the question? Oh, if it's like this, okay. Say it was like that. Okay, I don't think this is actually a compound, but let's pretend. Okay, this guy pulls with a strength of 2.5, and this guy pulls with a strength of 2.5. So these electrons will be equally shared between them. So there's no positive end, there's no negative end. Same thing happens here. So again, there's no positive end, no negative end. So this molecule altogether is nonpolar because none of the bonds have a dipole. Yes. What is H2O? Okay, so H2O, we have, what is H2O? It's water. I know you know it's water. Okay, so if we look at hydrogen, hydrogen has an electronegativity of 2.1, and oxygen is 3.5. That's going to give us a nice difference somewhere in this lovely unequal sharing zone. Yes? Now, if we look at the structure of water, we have oxygen, electron, 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 hydrogen's electron, electron, hydrogen's electron. Now bear in mind this is a Lewis structure, so it's flat, okay? This isn't really flat, but we're going to use this for now. And then we can redraw that as like that, yes. Oxygen, water is a bent molecule. We all know it looks like Mickey Mouse, yes? So we know that it is not a linear molecule. It does not go in a straight line, okay? We'll worry about why, again, a little bit later, okay? But assuming that it is bent like this, what would the bond dipole be? How would I draw the bond, the arrow here? Where would I put the arrowhead and where would I put the cross? Arrowhead goes towards the oxygen because oxygen is more electronegative. And then that goes there. Now, what about our other hydrogen and our oxygen? We draw another arrow. Okay. So if we look at this, everything's kind of pointing this way, yes? That would be our overall dipole would be that way. Okay? Right? Because I've got something going up and I've got something going to the left, which altogether means up and left. If you're doing physics and you're doing vectors, the molecular dipole is very similar to doing vectors. Okay? Now, to be honest, water doesn't really look like this. It's actually, do you guys remember if you have 4 areas of electron density around your atom, how would they arrange themselves so they're as far apart from one another as possible? In a tetrahedron. So we would have like literally like our little tripod with the thing going out the top, yes? 2 of these would be lone pairs, yes? And we can show them like this, like a little bubble with the 2 electrons in it. That's a lone pair, and that's a lone pair. And then we would have our 2 hydrogens here and here. These would be the bonding electrons in here. And all of those electrons are repelling each other and trying to get as far from one another as possible. And so we would have that tetrahedron, but it still results in that thing being bent. It's not a 90-degree bend like it would be if it were flat, but it's, you guys remember the number? It's 109.5 degrees. Yes. So like if I put iridium with silicon, let's look, iridium and silicon. Whoops. So iridium and silicon are about 0.4 from one another. So it would point towards the iridium. So you would draw this as the difference is 0.4. It's in that borderline area. So I would never give you something that's exactly 0.4 because that's, you're like, oh, is it polar? Is it non-polar? You know, like I'm not going to give you something where the difference is exactly 0.4. It's ambiguous. It probably has a little bit of polar character and a little bit of non-polar character. So, but iridium is bigger, so you would draw your dipole arrow like that. Yeah? Yes? Yes. They hang out because of math. It's like honestly, that's what it comes down to. Like, and we will talk about that when we get into looking at atoms. They do hang out 2 per orbital, because they do, and it has something to do with the fact that one of them's spinning one way and one's spinning the other way. They can do that. Small things are really weird, so we're just going to leave it for now. Now, Itamar had a question a long time ago, and I forgot about you. Yes? Fluorine with phosphorus. Yes. Well, some people put put this as 2. Do you know what I mean? Like it depends on which book you're looking at. Some people will put that as 2, some people will put it as 1.7. I would say, in general, if you have 2 nonmetals, just go with covalent. Yes? Okay, 2 nonmetals, don't worry about their difference in electronegativity. They are covalent. But if you see a difference like that, you can say that's a polar covalent because it's quite a big difference. Okay? And like I said, these numbers, it's like a spectrum. Yes? Like there's no actual cutoff line there. Somebody made these numbers and, you know, tried to describe them and things like that. Yeah. Yeah. Now, somebody else had a question as well. Yes. Okay. Yeah, and so if you've got a metal with a non-metal, just go ionic. Okay? And don't worry too much about it. It's more to do with distinguishing between non-polar and polar within the whole covalent family. It's a spectrum. I'm just going to go with that. It's a spectrum. Yes? I know, don't worry about it. Nobody's going to give any of those weird ones. Iridiums and the transition metals are a bit bizarre things, you know. Okay, hold on. We got Yoav and then Evan. Yoav? Yes. So we're on that. Okay, I'm going to come back to you. Yes. You're missing that. Oh, the electronegativity. It's at the back of the room on the little table there. Okay, so we were going to talk about, is that 6.3D? It is. Okay, activity series. This is on page 60. Oh, that's irritating. No, oxygen and things should be on there. I will find you a new one that has them on there. Okay. Oh, just because it's not a complete thing, I had to steal a diagram from somewhere, and obviously I stole an incomplete one. Yeah. Yeah. So, how are we feeling about electronegativity and polarity? Not bad? Okay. We're going to be coming back to it later. This was a preview. Yes? How are we doing? How did we do with synthesis, decomposition, single replacement? All good? Excellent. Today, we are going to take a look at double replacement, and specifically, we're going to be learning about the solubility table because all double replacement reactions take place in solution. Okay? So this, you should have your copy of it. It is also, if you need it, on page 66. Okay? Soluble, yes. Yes, yes, yes. You would get like a table with the electronegativities in it, or you would be given electronegativities, yeah. Yes. Yes. What is the meaning of the numbers? It just tells you how they are all relative numbers. They have to be, electronegativity is not something that has an absolute value. They're all measured in comparison to one another. Every atom is like, they put it together with another atom and they see which one pulls the electrons more, and then they measure that. Yeah, similar. Yeah, it's comparative, yeah. Of electronegativity, there isn't one. Okay, and every table you see will have slight differences in it. Okay, so this textbook, the numbers will be slightly different than that textbook, will be slightly different than that textbook. So electronegativity, the general trend is what's important. And you need to know that oxygen and nitrogen and fluorine, they're like the super electronegatives, okay? But other than that, don't get too hung up on the specifics. Yes? Yep. I think it's because, no, not really. No, there really isn't, no. It just happens to be, I mean, there's not a lot of non-metals to start with. And when you take out the noble gases, well, that takes out another of them. So there's only really 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them to start with, right? Yeah. And if you look at sulfur, it's the same as iodine, so yeah. We cannot measure electronegativities because they do not bond. And all the electronegativities, remember, are found by saying, how does this thing do when it bonds with something else? If they don't bond, you can't look at an electronegativity. We're just going to let that go for today, okay? Because I would like to get through some of the solubility stuff. Okay, it's okay. Shh. Soluble. Are we familiar with the term soluble? Yes, it means a substance will dissolve, in this case specifically in water. So, soluble means aqueous. Low solubility means it will not dissolve in water, and if it will not dissolve in water, then what state would it be? Solid. And in these cases, we're all talking about ionic compounds. And remember, what state are ionic compounds normally at room temperature? They're all solid. So we're looking at them and we're saying, is this thing in water going to actually dissolve, or is it not going to dissolve? So barium sulfate, we're going to look at this, and here's how we do it. We look up the anion. So we look and we say, okay, I've got sulfate. Here is sulfate. If I look for barium, my cation, and then I look across and I say, what is its solubility? Oh, it is low solubility. So that tells us that if I took some barium sulfate and it was in water, would it be dissolved or would it be solid? It would be solid, okay? So if it says low solubility, that means it is solid. Aluminum hydroxide. You look up hydroxide, you look up aluminum, and you look and you're like, I don't see any aluminum anywhere here. Aluminum is not listed. Oh no, whatever shall I do? Because it's not one of the listed ones, it falls in the all others category, yes? And that means if it's in all others, it has a low solubility. So again, aluminum hydroxide, if we put it in water, it will just stay a solid, okay? Copper 2 chloride. I bring this one to your attention on purpose, okay? Because people will look at this and they'll be like, copper, oh look. What's the problem with that? Yeah, this copper here is copper 2 plus, right? Because it's with 2 negative chlorides, right? Whereas this copper is copper 1. So copper 1 chloride is low solubility, but copper 2 chloride is in the all others category, okay? For this course and for grade 12, you will, when necessary, be given this table, Okay, you will have this table in front of you. The AP course, you do not get this table, but you only need to remember 3 things in AP, and that's that ammonium is soluble with everything, nitrates are soluble with everything, and the alkali metals are soluble with everything. Otherwise, they will simply tell you a precipitate of blah, blah, blah forms, and you'll know it's a solid. Okay, so they're not going to, they used to, back when I started teaching this, make you memorize a whole bunch of solubility rules. You really don't need to do that anymore. Okay, you need to recognize a few very simple, always soluble ones, and the rest of them, they'll just let you know if it's a solid or not. Okay? But we will use this table because it is used in the regular grade 12 course. Okay, it's used in the regular grade 11 course. Okay, so that was copper. These are the 4 things that you should memorize, especially if you're in AP. And even if you're not in AP, I recommend to all my grade 12 students who are, some of them seeing this for the first time, that they memorize these 4. Ammonium, you put it with anything, it is soluble. Acetate, you put it with anything, it is soluble. All of the alkali ions are soluble. You'll notice francium isn't there. That's because francium is radioactive and it doesn't stay around long enough to form a solid or not a solid. It just decays. And nitrate. Okay? So how about you guys take a moment and just read your table and figure out whether those are solid or aqueous if they are in water. Aqueous is when it says soluble. Oh, always soluble are ammonium, acetate, all your alkalis, and nitrate. These are always the other ones you need to look up on the chart. Either that or you have to do things like memorize that CBS, PBS. Like, you know, there's these little mnemonics you can use to memorize some of the other ones, but I'm thinking probably you don't want to do that. Lord knows I don't. Well, so you want your periodic table so you can know your charges of your anions. So make sure you got your periodic table as well. Yeah. I mean, I know it's here, but yeah. Always are they soldiers together? Yeah. You can't have like half of it soldiers and half of the other half. Right? So if I do this thing, yeah, you are thinking pretty. And if I remove all of why did they bring it like this? They didn't bring H2. No, it's H2. It has to be. Yeah. So if you go ammonium, everybody else knows.
When is it soluble? What do you mean, why do you do that? What are you talking about? Oh, yeah. Maybe it's a secret message.
No, but there's another one where
Okay. Yes. Huh? Oh. Oh. Oh my God. Okay, so apparently I can't do my alphabet. It's like so messed up. Yeah. A, B, C, D, E, F, G, H, I. There's two G's. Yeah, I'm so sorry. I'll fix that. Yeah, the answers are okay. 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 We're going to go now because I'm going to let you do 6.3F will be for homework. Okay, that's predicting the products of double replacement. And you can go through that and do that one on your own. Okay. Actually, do I even want you to do that? No, I don't. We're going to actually, oh, it's sideways. I have to fix that. So yeah, we're going to go and do this one. So this is on page 75. Acids, according to Mr. Arrhenius, who was a Swede, he had a theory about acids and bases, and what he said was that acids are substances that dissociate in water to yield electrically charged ions, one of which is the hydrogen ion. So if you have an acid and it's dissolved in water, it's going to dissociate in a similar way to ionic compounds. Remember when your ionic compounds go into water, they dissociate. So if you had sodium chloride and it was a solid and you dissolved it in water, it would become Na pluses floating around separately from Cl minuses, okay? So acids do a similar thing, and there are several definitions of acids. We are working right now with the simplest of them, which is from Mr. Arrhenius. So he said if we take HCl gas and we dissolve it in water, we're going to get hydrogen ions, and that's what makes it an acid. If we take hydrogen bromate and we dissolve it in water, then we get H+ ions, and so that is now an acid. Although acids are molecular compounds, they are covalent compounds, they still dissociate in water to form ions. I know it makes me unhappy too. Don't be mad at me. It's just the way life is. Okay? They are covalent. And yet, what do? They dissociate to form ions. So, here we have hydrogen chloride gas. Yes, they are molecules. And therefore that is molecular. Dissolved in water, we have chloride ions. They float separately. Molecule, it's a molecule, so therefore it is molecular. So the chlorides float separately from the H+. Everybody's floating around separately. Yes? Okay. Bases, Mr. Arrhenius said, they dissociate to yield hydroxide ions. And so basically a base is any ionic substance that contains hydroxide, because what contains hydroxide? It's ionic substances. So these are going to be ionic compounds where the anion is OH minus, and I forgot a bracket here, oopsie. Okay. So you can see, just like the acid, if we had sodium hydroxide, which is a solid, it goes into the water and the hydroxides float around separately from the sodiums. Okay, and there's a little picture. Those would be our sodiums. That would be Na+. And the hydroxide, this would be OH minus. Okay. Mr. Arrhenius also said that soluble salts dissolve to form ions, and you can see that's what we've talked about already. Yes? Yes. It's just a proton. And in fact, in grade 12, we start referring to them as protons. Yeah? Yeah. Okay, so there's a few little exercises that let you classify each of these as acids, bases, and salts, and then it lets you write the dissociation equations for those. And we have like, what, 2 minutes? 4. We have 4 minutes. So your homework Page 69. to 73. What? Oh yeah, you could do say 76 as well. Well, otherwise I would have forgotten about it altogether and you'd never have practice with it. Right? That would be like, and now it's test time and you're like, I don't know.